Swayam Prabha. Digital India. Educated India.
In the last lecture, we started with the virtual work equation for these beams with piezos, and from those equations we saw how we can get a governing equation that we are familiar with. Now we will we will see how by starting from the same virtual work equation we can get a governing equation in a different form. So, again we will look at equilibrium equation, but we will derive it in a different form. So, after we start with the virtual work equation, we obtained this form. So, if I do not shift the derivatives here, if I do not do the integration by parts, we can, if we retain it as it was, we have it here, and rest of it we know how to get. Now, what we will do is, instead of integrating by parts here and here, we will do the integration by parts here and here, and that will give us a governing differential equation in a different form. So, if you look at the first term, which was our integral E A total if I integrate by parts, it gives me E A total del u 0 by del x multiplied by integral of this, and integral of this but is nothing but delta of u 0, and it is evaluated at x equal to 0 and L, and then we have minus of differentiation of this. So, del x of E A total del u 0 by del x multiplied by integral of that. So, delta of u 0 0 to L dx. So, we can see it here, these terms. So, these terms comes from this. Similarly, we can do the same thing for the next term, where we have delta of del u 0 by del x multiplied by E s total into del 2 w by del x 2. After we do the integration by parts, we get this term, and then we had N p multiplied by delta of del u 0 by del x, and that were integrated from 0 to L. So, if I do integration by parts here, it gives me N p multiplied by the integral of this, which is delta of u 0 0 to L minus del n p by del x into variation of u 0, and which we can see here. So, this had a negative sign before, so that is why it was negative, it is positive, what we see here. Then we had a term like E s total multiplied by del u 0 by del x multiplied by variation of the second order derivative of w, and this was integrated from 0 to L, and if I integrate this by part, that gives me Es total del u 0 by del x, variation of delta w by del x, which is evaluated from at the limits 0 and L, and then minus I would have derivative of this and integral of this. So, now the other term that I get as minus I am writing here. Multiplied by variation of del w by del x. But again if I integrate this by parts, this would give me minus del by del x E s total multiplied by variation of w, and that gets evaluated at 0 and L, 0 to L, and then plus this differentiated twice E s total. So, here this term is missing, it is E s total del u 0 by del x multiplied by delta w, and here we have the same thing, but differentiated once more multiplied by delta w dx. So, that is how we get this term and this term. Accordingly, we can find out rest of the terms by doing the integration by parts, and we get this entire expression. Now, if we look at this entire expression, we can see that the variations are in del u 0 w del w by del x, and that is all. So, if we separate out the components that are multiplied with delta of u 0, delta of w and delta of del w by del x, we get this. In this expression, we have these two terms that are integrated, whereas these expressions are, these three expressions are all defined at the boundaries. Now, if we look at these boundary terms, we can see that this is nothing but our n, normal force n. So, this thing inside the bracket is normal force n. Why? Because we have seen so far that E a total plus E s total multiplied E a total del u 0 by del x plus E s total del 2 w by del x 2 minus n p minus n equal to 0, which means that this equal to n. So, this is equal to n here. Similarly, using the same reason, this is my m, and this is nothing but del m by del x, which gives me shear force. Now, again we can make similar argument and we can say that these terms are 0 for our case, because at x equal to 0 we have the axial displacement specified, which is u 0, which means that delta of u 0 is 0, at the other end the normal force is 0. Similarly, here we have the slope del w by del x specified, which means the variation of the slope is 0 at this end, and at x equal to L we do not have the bending moment. So, the bending moment is 0 at x equal to L, and at x equal to 0 we have the displacement specified. So, del w is 0 here, and at x equal to L we do not have any shear force. So, that helps me get rid of all these terms, and we are left with only this and this. And again we know that delta u 0 and del w are independent and arbitrary variation, which tells me that these integrands must be individually 0. And from that same argument we can say that this is our one governing differential equation and this is our other governing differential equation. So, we get the governing differential equations in a different form now. If I compare this form with our previous form, the difference is that while getting the previous form we did integration by parts in these terms where NP and MP were present, where Px and Pz were present, whereas here we did integration by parts in the other terms, and there it was written in terms of variation of epsilon 0 and kappa. Here it is written in terms of u 0 and w, and from there we get these two equations. Now, we will see using these two equations how we can get the solution to the problem. Now, these two equations are now written in a compact form as this. So, here we have this operator. So, u 0 comes here and it gets operated here, w comes here and it gets operated here, and we get the first equation. Similarly, u 0 comes here and w comes here and we get the second equation. And we are going to solve it by using a technique named the Galerkin technique. So, let us to apply the technique again, let us assume that we have u 0 as this. So, u 0 is written as a combination of this product, and within this product we have phi and q. So, phi u is chosen, phi u I is chosen function to approximate u 0, and similarly phi w I is chosen to approximate w. If we can choose in such a way that they satisfy both essential and natural boundary conditions, I mean the geometric and force boundary condition, that is good, but at the bare minimum they should satisfy the essential boundary conditions. So, these phi's are all known to us because we are choosing them, and they are being multiplied with unknown constants q u j, q e y and this q w j. Now, q u I, q w j are unknowns to be found out. Now, we have assumed that our u 0 has this m number of terms and w has this n number of terms. So, the vector q u ranges from 1 to m and the size of the vector q w is n. Now, we can write a vector u which has u 0 and w, and then we can write it in terms of these phi's and these q's as this. Here we have first m terms which is populated with these q u's, and then rest of the n terms are 0, and here we have first m term 0 and then rest of the n terms populated with these q w's. So, this is of size 2 multiplied by m plus n, and this is of size m plus n multiplied by 1. Now, we can call this entire vector as one q vector with size m plus n. So, within this q vector, the first m number of q's are q u's and rest of the n number of q's are q w's, and it is multiplied with the same thing. So, in a compact way we can call this as phi matrix multiplied by q matrix. So, this is our phi matrix and this is our q vector. So, again the governing equation rewritten here. So, if we put the approximations of u 0 and w, so that becomes our phi multiplied by q. Now, because they are approximations, they may not be exact with u 0 and w. So, if I take the right hand side to the left hand side, and if we substitute u 0 w vector as q as phi q, then we can say that after this entire thing may not be exactly 0, because phi q may not be exactly equal to u 0 w. So, there can be some error which is remaining, and that error is this. So, the close we are to the real value of u 0 and w, less is the error. Then what we do is we multiply this error function by this approximation phi's, and then so if we go back to our phi vector. So, this is our phi 1, this is our phi 2, this is our phi 3, phi m and so on, and we can go up to phi n. So, we may say that we may like to call this as our phi 1 vector, and we can go on. So, this is our phi m vector, and we may call each of them as a vector, and we can say that this phi vector consists of, this phi matrix consists of this capital phi matrix consists of all these small phi vectors. Now, in this error function, if I multiply the what we are doing here, if I multiply the ith phi, the transpose of that with the error function, and then integrate from 0 to L and equate that to 0, and we can do it for all these phi's. So, that gives me total m plus n number of equation, and those m plus n number of equations would have these q's as the unknowns, and that will give me, so it will give me m plus n number of equations with m plus n number of unknowns, and that can be written in a matrix form as this. Now, this we call stiffness matrix and this we call force vector. In the stiffness matrix, the generalized ith component can be written as this. So, Kij is equal to phi I multiplied by this matrix multiplied by phi j. So, we know that it is 1 by 2 because the ith column of phi is 2 by 1, and similarly this is 2 by 1 and this is 2 by 2. So, entirely after this multiplication, this gives me one value, the ijth value of the kth matrix. Let us assume that our phi j, let us assume that we are taking from our phi matrix, we are taking this as I and this as j. So, let us assume that I is equal to 1 and j is equal to 2. So, in this case it would look like this: phi u 1 0 multiplied by this vector del by del x E A total del by del x, and then we have this phi u 1 and 0. So, when I multiply this row with this column with this row, I have del x of E A total del phi 1 del x plus 0, and here I have del 2 del x 2 of E S total del phi 1 del x as 0. So, let us as we said, let us assume I is equal to 1, j is equal to 2. So, it is 2. So, that gives me phi 1 0, and here we have del x of E A total del phi u t by del x, and here we have del 2 by del x 2 E A total del phi u 2 by del x, and of course, this has to be integrated from 0 to L. This also has to be integrated from 0 to L. Again we multiply this row with this vector, and after we multiply we are remaining with only one term. So, this multiplied by this term multiplied with by this term, that will give me just one value, this multiplied by 0 will give me 0. So, finally, we will get just one value of we will get 1 by 1 term, which is our k I j. So, in this particular case, which is k 1 2. So, accordingly we can just put any I here and any j, any I here and any j here, and accordingly we will get the k I j, and this entire matrix would be populated. Similarly, when I find out phi I, this becomes the expression. So, phi I is multiplied with del n p by del x and del 2 m p by del x 2, and then we have phi I transpose. So, here also we have phi I transpose, and here also we have phi I transpose multiplied with minus p x p z vector. Now, generally while evaluating this, we do not directly evaluate this, we shift the derivatives here also by integrating by parts, and then we see that the boundary terms goes 0 and the rest of the integral we evaluated. So, instead of the differentiation being here, we get the differentiation here and we evaluate. So, later on when we do an example, we will see it in more details how the derivative is shifted and how this term is evaluated in a better way. So, with this we get the K matrix and the force vector, and by solving we get our Q, and once we get our Q, so we have QU, we have QWs. So, we get QU, QWJ from here, and then we put it back in our approximation, that U0 as a function of U is summation of phi ui into QUI, and W as a function of x is equal to phi Wj into QWJ. So, we just put it here and we put it here, and that gives us the desired solution. So, we get our solution. So, that is one way to solve these differential equations. So, here we started with the differential equation, and then we multiplied them by each of these approximation functions, and finally, this differential equation was converted to a set of algebraic equations, and then by solving the algebraic equations we get our solution. So, with this I would conclude it here. We will look into some other techniques, other similar techniques in the next lecture. Thank you.